Can a transformer actually understand the shape of random data without ever being trained on it? I know, it sounds totally contradictory, right? We're so used to generative AI models needing massive mountains of pre-training on specific datasets just to understand a single distribution. But what if a transformer could look at a handful of scattered, completely novel data points and just instantly deduce the underlying mathematical rules governing them? Welcome to the Explainer. Today, we're unpacking a really fascinating new research paper titled DiScoFormer, Bridging Transformers and Non-Parametric Statistics. We're going to explore how researchers have successfully bridged this massive gap between the modern, highly scalable architecture of transformers and the foundational classical world of non-parametric statistics. It's basically a fusion of two entirely different paradigms in machine learning, and honestly, the results are pretty mind-bending. So, here's our cognitive roadmap for today. We'll start with the core statistical problem, explore the Great Divide, and then meet the DiScoFormer. After that, we'll unpack how attention is actually kernel smoothing, look at the empirical proof and scaling, and wrap things up with some real-world applications. All right, Section 1, the core statistical problem. Let's establish exactly why this research even matters in the first place. You see, the foundational problem in statistical inference and generative modeling is guessing the underlying shape and flow of data from just a few isolated, scattered points. It's kind of like throwing a handful of darts at a dartboard while blindfolded, and then trying to figure out exactly where the bullseye is and what the entire board looks like based purely on where those few darts landed. Mathematically, we're trying to estimate two critical things here. First is the probability density, which we call F. That tells us the shape or the concentration of the data. And second is its score, which is the gradient of the log density. You can think of the score as a set of little vector arrows pointing toward where the data is the most dense. Nailing these two estimates from raw, scattered samples is absolutely crucial. It's the skeleton key for unlocking everything from Bayesian inference to simulating really complex fluid dynamics in physics. Section 2, the Great Divide. Trying to get these metrics right has created a massive roadblock in the field for a long time. For years, researchers have been stuck with a really harsh, uncompromising trade-off. On one side, you have classical non-parametric methods like kernel density estimators, or KDE. Now, KDE is great because it's a true general-purpose tool. It works broadly across different distributions without needing to be retrained. But, and it's a big but, it suffers heavily from what statisticians call the curse of dimensionality. As your data gets more complex and moves into higher dimensions, the volume of that space just explodes. The data gets incredibly sparse, causing KDE's accuracy to completely tank while its computational costs skyrocket. On the other side of the divide, we have modern neural score matching. This is the powerhouse tech behind today's massively popular diffusion models. They achieve unbelievable precision in those tricky high-dimensional spaces. But here's the catch. They are transductive. That means you have to go through expensive, computationally tedious retraining for every single new target distribution. You can't just plug them in and use them off the shelf. Section 3, introducing DiScoFormer. Let's look at the breakthrough that acts as the ultimate bridge between these two worlds. Meet the DiScoFormer, which stands for Density and Score Transformer. The real secret sauce here is how it handles the geometry of the data. By treating scattered data samples as a sequence rather than a fixed grid, the transformer natively provides permutation equivariance, and then by adding a specialized affine normalization layer, the model achieves affine equivariance. Basically, what that means is if you shift, rotate, or stretch your data, if the underlying geometry fundamentally changes, the DiScoFormer perfectly adapts its predictions. It doesn't miss a beat. It maps the raw samples directly to density and score values in a single forward pass. So what we end up with is a universal, highly scalable plug-in estimator. It operates with the precision of a neural network, but it doesn't need that constant, tedious retraining for new distributions like the modern score matching methods do. Section 4, attention is kernel smoothing. This brings us to the real aha moment of the paper, where the math gets genuinely exciting. The researchers actually proved analytically that the transformer isn't just some opaque black box making lucky guesses. The self-attention weights inside the transformer actually perfectly recover classical normalized kernel density estimation weights. When you look at visualizations comparing the transformer's average attention directly to a normalized KDE matrix, they are virtually identical. In fact, the data reveals a near-perfect correlation of 0.93 between the two. What this proves is that the cross-attention equation natively running inside these modern AI models is fundamentally mirroring a highly optimized, reweighted Gaussian kernel smoothing equation. The network literally learned the foundational rules of classical statistics entirely on its own. How cool is that? And because it's a multi-head transformer, it doesn't just apply one rigid, static smoothing rule across the board. When we break it down and look at the individual attention heads, we see them dynamically specializing directly from the data. Some heads act like short-sighted lenses, learning to look exclusively at close-range and mid-range interactions. Meanwhile, other heads specialize in far-range interactions, checking out those distant data points at the very edges of the distribution. Some even specialize in looking in specific geometric directions. So, rather than having a human engineer manually tuning a kernel bandwidth, the multi-head attention acts as this highly flexible, multi-scale kernel that autonomously adapts itself perfectly to whatever data geometry you throw at it.
Section 5, Empirical Proof and Scaling. Theory is fantastic, but let's look at the hard evidence to see if DiScoFormer actually beats classical methods in practice.
Let's think about mapping out score estimation in a 2D space. Remember, the score represents those gradient arrows pointing to denser clusters of data. When we compare the absolute ground truth of a dataset against the transformer's predictions, the model's estimations map almost flawlessly to the true data flow. The error margin is incredibly tiny. But when we evaluate classical KDE, well, right in the dense center of a data cluster, it does an okay job. But out in the sparse outer regions, where the data is scarce, classical KDE completely loses the plot. It fails to capture the true geometry, sending the gradients off in entirely wrong directions. This massive victory really becomes obvious when we scale up beyond simple 2D data into higher dimensions. Like we mentioned earlier, the curse of dimensionality hits classical methods hard. In a 10-dimensional space, the DiScoFormer maintains incredibly tiny error margins, improving down to about 2% error as you give it more samples. But classical KDE, as the sample size grows to try and capture that massive high-dimensional volume, KDE literally runs out of memory on a massive 48GB GPU. It just crumbles under the mathematical weight. The transformer, however, breezes right through it, scaling gracefully exactly where classical kernels completely collapse. Now, the true, undeniable test of a plugin estimator is how it handles out-of-distribution generalization. Keep in mind, the DiScoFormer was only ever trained on Gaussian mixture models, which are basically just combinations of smooth, standard bell curves. But the real world is rarely that clean, right? Well, when researchers threw completely unseen, non-Gaussian distributions at the model, like the heavily peaked Laplace distribution or the notoriously tricky, heavy-tailed student T distribution, the DiScoFormer didn't even flinch. It easily adapted right out of the box. It accurately estimated their scores with remarkable precision without a single step of retraining.
Finally, Section 6, Real-World Applications. Why does all this math actually matter for the real world? Let's get into it.
Because it completely sidesteps the need for per-distribution retraining, DiScoFormer serves as an incredibly fast, off-the-shelf oracle for complex physics and statistical simulations. Whether you're calculating differential entropy, estimating Fisher information to measure variance, or running particle methods to solve complex kinetic equations for plasma simulations, you absolutely need highly accurate score gradients at every single time step. Traditionally, doing this with neural nets meant you had to pause your entire simulation to retrain the model over and over as the data shifted. Now, you just plug in the DiScoFormer and let the simulation run seamlessly. It's a real game changer. The ultimate payoff is seen in something called score-debiased KDE. See, standard KDE has a smoothing bias. It inherently blurs and washes out the true sharp shape of the data. But if you know the exact score, you can intelligently push the data points perfectly back into place before you apply the smoothing. This creates a razor-sharp density estimate. By feeding the transformer's learned score directly into this debiasing process, the resulting density heat maps match the ground truth with stunning precision. It dramatically outperforms the blurry standard methods. It essentially cleans the lens of our statistical tools, giving us a perfectly clear picture. By proving that the self-attention mechanism is actually a highly advanced data-adaptive generalization of kernel smoothing, this paper completely reframes how we should view modern AI architectures. They aren't just parlor tricks or memorization engines for generating text or images. They are universal math solvers natively attuned to underlying geometric symmetry. Which leaves us with a genuinely fascinating question to ponder. If attention mechanisms can seamlessly adapt to classical non-parametric statistics right out of the box, what other foundational rules of mathematics and physics will transformers conquer next? It's definitely something to think about. Thanks for joining me on this explainer. And as always, keep learning.